Welcome to a detailed visual guide to the multivariate normal distribution. This is the most important continuous distribution for random vectors in statistics, signal processing, and machine learning. A d-dimensional normal is fully specified by a mean vector mu and a positive definite covariance matrix sigma. Together they determine the center, spread, and orientation of a bell-shaped density in multi-dimensional space. In the next sections we will build intuition through pictures rather than algebra alone. We will compare three covariance structures, decompose sigma into rotation and scaling, watch linear maps transform Gaussian clouds, and derive marginals, conditionals, products, and change of variable rules. Each idea has a direct application, from Gaussian mixture models and PCA to Kalman filters and Bayesian neural networks. Section 1, Types of Covariance Matrix. The simplest case is spherical covariance, sigma equals sigma squared times the identity matrix. All directions have the same variance and the variables are uncorrelated. Geometrically, density contours are perfect circles. Isotropic Gaussians appear in k-means clustering, radial basis kernels, and as a simplifying assumption when you have little data. Next, diagonal covariance. Sigma has different variances on the diagonal but zeros off diagonal. The cloud stretches along the coordinate axis wider in x1 than x2 here, yet still with no correlation. Naive Bayes classifiers assume diagonal covariances for tractability. Finally, a full covariance allows off-diagonal terms. Positive correlation pulls the cloud toward a tilted ellipse. Compare the three panels: round, axis-aligned, and rotated. The same mean, but very different dependence. The off-diagonal entry controls Pearson correlation ρ. Ρ equals sigma 1,2 divided by the product of standard deviations. Here ρ is about 0.75. When x1 is above average, x2 tends to be above average as well. Positive ρ tilts the ellipse upward, negative ρ tilts it downward, 0 ρ gives an axis-aligned ellipse. Correlation is scale-free, whereas the raw covariance sigma 1,2 depends on units. Section 2, Decomposing the Covariance Matrix. Every positive definite sigma admits an Eigen decomposition, sigma equals q lambda q transpose. Q is an orthogonal matrix whose columns are eigenvectors, the principal directions of the cloud. Lambda is diagonal with eigenvalues that measure variance along those directions. This is the same mathematics behind principal component analysis. The yellow arrows visualize the eigenvectors scaled by the square root of eigenvalues. Longer arrows mean more spread in that direction. Equivalently, sigma equals LL transpose via the Cholesky factor, where L is lower triangular. We can sample a standard normal Z, then set x equals mu plus LZ to obtain x with covariance sigma. Decomposition turns a correlated vector into independent coordinates plus a linear map. Density contours are ellipses of constant Mahalanobis distance. The squared distance d squared equals x minus mu transpose sigma inverse x minus mu. Each nested ellipse you see corresponds to a different value of d squared. Points on the same contour are equally likely under the density. Mahalanobis distance generalizes Euclidean distance by accounting for scale and correlation. It is the natural metric for Gaussian anomaly detection and discriminant analysis. Whitening is the inverse idea: transform data so the covariance becomes the identity. If L is the Cholesky factor with sigma equals LL transpose, then Z equals L inverse times x minus mu has zero mean and identity covariance. On the left, correlated data; on the right, the same points after whitening, a round, uncorrelated cloud. PCA pre-processing in many generative models begin with this step. Section 3, Linear Transformations. One of the most powerful closure properties of the normal family is this: if x is multivariate normal, then y equals ax plus b is also multivariate normal. The new mean is a mu plus b. The new covariance is a sigma A transpose. No matter how you shear, rotate, or scale space, a Gaussian cloud remains Gaussian. On the left is the original full covariance cloud. On the right is the same samples after applying matrix A with a shear component. Notice the ellipse rotates and stretches, but the point cloud stays elliptical. This formula drives Kalman filter prediction steps, weight propagation in linear networks, and whitening transforms in data preprocessing. Any non-singular linear map decomposes into rotation, scaling, and another rotation, the singular value decomposition. First rotate the spherical cloud without changing its shape. Then stretch along the new axis. Finally rotate again to reach a general full covariance. This three-step picture explains why every Gaussian cloud is an ellipse, and why PCA axes align with the directions of maximum variance. Section 4, Marginal Distributions. The marginal density of a subset of coordinates is obtained by integrating out the rest. For a bivariate normal, the marginal of x1 is one-dimensional normal with mean mu1 and variance sigma 1,1. The marginal of x2 uses sigma 2,2. Crucially, both marginals are Gaussian even when x1 and x2 are strongly correlated. The curves above and to the right are those marginal densities projected from the joint cloud. If you only observe x1, you lose information about how x1 covaries with x2. In probabilistic graphical models, marginalization corresponds to summing out hidden nodes. For jointly normal variables, that operation always lands back inside the normal family. In matrix notation, partition the mean and covariance into blocks. If you only care about the first k coordinates, the marginal covariance is simply the top left k by k block of sigma. No integration formula needed, the block itself is the answer. In machine learning, when we observe only part of a Gaussian vector, this block structure tells us exactly how much uncertainty remains in the observed subvector. Section 5, Conditional Distributions. Instead of integrating out x2, we can fix it to a particular value y and ask what x1 looks like. For the bivariate normal, the conditional x1 given x2 equals y is again normal. Its mean is a linear function of y with slope sigma 1,2 divided by sigma 2,2. Its variance sigma 1,1 minus sigma 1,2 squared over sigma 2,2 is strictly smaller than the marginal variance whenever correlation is non-zero. The red dashed line marks the slice where x2 equals 1.2. Along that slice, the conditional density of x1 is the red bell curve drawn in the plane. This is exactly the regression line of x1 on x2 for Gaussian data. Gaussian process regression, Wiener filters, and Kalman update steps all reuse this conditional normal formula. Slide the slice to a different value of x2 and the conditional mean moves along the red regression line. Here at x2 equals negative 1.5, the conditional bell shifts left. The conditional variance stays the same regardless of which value you condition on, only the mean slides. That constant conditional variance is a special feature of the normal distribution. The Schur complement gives the conditional covariance in block form. Sigma 1,1 given block 2 equals sigma 1,1 minus sigma 1,2 sigma 2,2 inverse sigma 2,1. This is the matrix version of the scalar formula we used earlier. It generalizes immediately to high dimensions and underpins the update step in Gaussian graphical models when new variables are observed. Section 6, Product of two normal densities. When two Gaussian factors depend on the same variable x, their product is proportional to another Gaussian. This is the algebraic heart of conjugate Bayesian updating. Multiplying a prior by a likelihood produces a posterior that is still normal before we even normalize the constant. The blue and green curves are the two factors. The orange curve is the renormalized product. Its mean is a precision-weighted average of mu1 and mu2, and its variance is smaller than either factor alone. Combining information tightens belief. You see this in one-dimensional Kalman updates, ridge regression penalties, and every closed-form Gaussian Bayes filter. Precision, the inverse variance, makes the product rule especially clean. If tau1 equals 1 over sigma 1 squared and tau2 equals 1 over sigma 2 squared, then the product precision is tau1 plus tau2, and the product mean is the precision-weighted average we saw before. Working in precision space turns multiplication into addition, which is why Kalman filters and Gaussian belief propagation track precisions internally. Section 7, Change of variable. If y equals g of x and g is 1:1 and smooth, densities transform by the Jacobian. The formula py of y equals px of g inverse y times the absolute derivative of the inverse. Intuitively, probability mass stretches or compresses when coordinates are reparametrized. Example: y equals 2x plus 3 with x standard normal. The mean shifts by 3. The standard deviation doubles because the derivative of the map is 2. In multiple dimensions, the scalar Jacobian becomes the determinant of the matrix of partial derivatives, and for linear maps y equals ax we recover sigma y equals a sigma x a transpose, linking this section back to our linear transformation rule. In multiple dimensions, the Jacobian determinant generalizes the scalar derivative. If y equals g of x with a 1-to-1 differentiable map, then py of y equals px of g inverse y divided by the absolute determinant of the Jacobian. For a linear map y equals ax, the Jacobian is a itself, and we recover the sigma y equals a sigma x a transpose rule from section 3. Nonlinear maps such as polar coordinates use the same formula with a position-dependent Jacobian. A special fact for Gaussians: if x1 and x2 are jointly normal and uncorrelated, they are independent. That is false for most distributions, but true here because the joint density factors into a product of marginals when the cross-term and the exponent vanishes. Diagonal covariance therefore means not just zero correlation but true statistical independence, a distinction that matters when designing generative models and factorized variational approximations. Section 8, Summary. The covariance matrix controls geometry, spherical, diagonal, or fully correlated, parameterized by variances and correlation ρ. Spectral, Cholesky, and SVD decompositions explain rotation and scaling. Mahalanobis distance defines elliptical contours, whitening standardizes the cloud. Linear maps preserve normality while updating mean and covariance. Marginals read off blocks of sigma, conditionals use the Schur complement. Products add precisions, change of variable rules use Jacobian determinants. For Gaussians, uncorrelated implies independent. Applications span the full machine learning stack. Gaussian mixture models cluster data, linear regression assumes Gaussian noise, Kalman filters propagate normal beliefs over time, variational autoencoders often use Gaussian latents, and diffusion models build on Gaussian noise schedules. Mastering the geometry of sigma is the foundation for all of these methods. The multivariate normal earns its central role because so many operations, integration, conditioning, linear maps, and multiplying factors keep you inside the family with closed-form answers. Thank you for watching. Try editing the covariance matrices in the scene code to see each visualization respond in real time.